All right, welcome everyone to this deep dive. We've got some really interesting source material you shared, focusing on some core mathematical ideas.
Yes, we're going to unpack relations and mapping today. Foundational stuff, really, about how we describe connections.
And the source material lays it out quite nicely, like a chapter guide with definitions, examples.
Uh-huh. Our goal is basically to pull out the essentials. What's an ordered pair? What makes something a relation? And then what's this special case called a mapping?
Let's get into it.
Ah,
So the most basic piece seems to be the ordered pair.
exactly. It's just two things, say x and y, written like xy. But the key, and it's right there in the name, is order.
The order is critical. The source makes it clear xy is not the same as yx. Unless x and y happen to be identical, position matters.
Right. Think of coordinates, maybe, or the example, Mita 22, Akshay 20. It's a set of pairs, each linking a name to an age in a specific way.
Meta is the first component, 22 the second. And the rule for equality is super strict.
Yeah, AB equals CD if and only if A equals C and equals D. Both have to match perfectly. No wiggle room.
Okay, so that's the building block. How do we get from a pair to a relation?
Well, a relation is basically an association. It's a way of linking objects from potentially two different sets based on some shared property or rule.
Like the non-math example you pulled out, Peter's the son of John. The relation there is the son of. It connects Peter to John.
Precisely. It's the connecting property. And we can show these relations in a couple of ways the source mentions.
Okay,
First is the roster form. You just list out all the ordered pairs that actually satisfy the relations rule.
like a list of results.
Exactly. The second way is more visual, an arrow diagram. You draw the two sets and then arrows going from an element in the first set to an element in the second, but only if they're linked by the relation.
Let's use example 3 to make that concrete. We
Yeah.
have set A 1, 3, 4, 5, 6, 9, 10, and set B 0, 1, 2, 3.
And the relation bar is square of going from A to B.
Okay, so we need pairs AB, where A is from A, B is from B, and A is B squared. Which ones work?
Let's see. 1 in A is 1 squared from B. 4 in A is 2 squared, and 9 in A is 3 squared. That's it from set A.
Right. The others in A, like 3, 5, 6, 10, aren't squares of anything in B. So the roster form is 1, 1, 4, 2.
9, 3. Perfect. And the arrow diagram would just show those three connections visually. An arrow from 1 to 1, 4 to 2, and 9 to 3.
Now, from that roster form, we can define the domain and range.
Yep. The domain is simply the set of all the first elements in those pairs. So 1, 4, 9.
And the range is the set of all the second elements, which would be 1, 2, 3.
Exactly. It's just the elements that are actually used by that specific relation.
Okay, that seems clear for relations in general.
Yeah.
But you mentioned a special type, mapping.
Right. A mapping, sometimes called a function, is a relation from a set A to a set B, but it has stricter rules. Two main conditions, really.
Condition 1.
Every single element back in set A must be related to one and only one element in set B. Uniqueness is key here.
Every element in A has to participate, and it can only point to one thing in B.
Precisely. And the second condition, which the source notes and is sort of another way to view the first one.
Is that if you look at the roster form, no two ordered pairs can have the same first component.
Yeah, because if you had, say, A, B1, and A, B2, that would mean A points to two different things, B1 and B2, violating the only one rule. So checking for unique first components is a good test.
Let's look at example 7 where things don't work out. A 5, 6, 7, 8, B 7, 8, and the relation is less than.
Okay, so what pairs A, B satisfy A is less than B? We get 5, 7, 5, 8, 6, 7, 6, 8, and 7, 8.
Right. Now, why isn't this a mapping from A to B?
Well, first off, look at element 8 in set A. Is 8 less than 7? No. Is 8 less than 8? No. So 8 isn't related to any element in B.
So it violates the every element of set A must be associated condition.
Exactly. That's reason 1. And reason 2, look at element 5 in A.
It forms two pairs, 5, 7, and 5, 8. It's associated with two different elements in B.
Right. Same problem with element 6, which forms 6, 7, and 6, 8. This violates both the only one element in B rule and the no two pairs with the same first component rule.
So this is less than example is definitely a relation, but it fails the mapping test on multiple counts.
Makes the distinction pretty clear, I think. Every mapping is a relation because it's a set of ordered pairs. But not every relation meets the stricter conditions to be called a mapping.
So wrapping this up, what's the big takeaway for you, the listener?
It's about precision. Ordered pairs give us precise links. Relations let us group links by a rule. Mappings ensure those links are well-behaved, predictable, unique outputs for every input.
And this isn't just abstract math, right? This structure appears everywhere. Think about databases, coding functions, even just organizing information logically.
Absolutely. Is your list of users and their primary email address a mapping? It should be. If one user has 2 primary emails listed, your relation isn't a mapping, and your system might break.
So we've journeyed from the basic ordered pair through relations, domain, range, and finally to the specific requirements of a mapping, drawing directly from the material you shared. It's a framework for thinking clearly about connections.
It really is. And here's something maybe to chew on.
Go on.
Think about the relationships you deal with constantly, maybe in data you analyze, processes at work, or even social networks. How many could be described as relations? How many should be mappings?
And what are the real-world consequences when something that ought to function like a mapping doesn't? When one input leads to multiple outputs, or some inputs lead nowhere.
Exactly. What does that failure tell you about the system itself? Something for you to mull over.